Hi students, in the previous two videos we discussed about focal length of a lens and also what is the magnification in terms of image distance and object distance. Now in this video we are going to find out what is power of a lens and what is the effective focal length if lenses are combined. So let us first see what do you mean by power of a lens. Now power of a lens is defined as tangent of angle by which a lens converges or diverges a beam of light falling at the unit distance from the lens, from the optic center of the lens. This is defined as tangent to the angle by which a lens converges or diverges a beam of light falling off at unit distance from the optical center of the lens. So imagine you have a lens. Now this is the optical center, and a ray of light is passing through the lens. This is at unit distance from the optical center, so h is equal to 1. Now after passing through the lens, what happens? While passing, it undergoes refraction and it passes through the focus, since the incident ray is parallel to the principal axis. Now this angle is delta and this angle is also delta. Now from the triangle, we will call this point as M. And this point as capital F. Then from the triangle MOF, tan delta. This is the lens. This is the optic center. This is the ray of light undergoing refraction, passing through the focus. Now this angle is delta and also this angle is delta. This is we take as h and this point is M. So from the triangle MOF, tan delta is opposite side by adjacent side. So tan delta is MO divided by OF. Now what is MO? MO is h. And OF means distance from the optical center to the focus is taken as the focal length, small letter f. So h divided by f. So tan delta is h divided by f, but we have defined according to the definition the value of h is equal to 1. So we get tan delta, which is the power, is equal to 1 divided by Fy, since h is equal to 1, unit distance from the optical center. So h is equal to 1, and hence we can define power as power can also be defined as reciprocal of focal length. And the unit of power is, what unit of power is? Diopter, denoted by the letter capital D, and 1 diopter is 1 meter raised to minus 1, while P is equal to 1 by F. So when P is 1D, we will get F is as 1. Yeah. So 1 diopter is 1 meter raised to minus 1. Now we know the lens maker's formula which relates the focal length with the refractive index and radius of curvature as 1 by f is equal to mu minus 1 into 1 by r1 minus 1 by r2. This is the lens maker's formula relating the focal length, refractive index and radii of curvature. Now 1 by f is what? 1 by f is equal to power. So this can be written as P. Now if you look at this equation, it is clear that mu is the refractive index of the medium, of the lens, of the metal from which the lens is made, and R1 and R2 are radii of curvature. So mu depends, depending upon the lens, it will be having a constant value mu minus 1. The term which is varying will be R1 and R2, isn't it? So if you take a convex lens, you know lens is made from a sphere, so it is a part of a sphere. Each spherical surface is a part of a sphere. Now for the first refracting surface, this is the first refracting surface, center of curvature will be somewhat here, isn't it? So R is taken in the direction of light, which means R1 is positive. It will be having a positive value. Okay, and the second refracting surface is this, and this is the sphere from which it is made, which means R2 is taken in this direction because center of curvature of this spherical surface is somewhat here, isn't it? Which means R2 is negative. So for a convex lens, this is very important when you do problem. For a convex lens, R1 is positive whereas R2 is negative. Now it will be having a value, fixed value, and using the sign convention, if you apply this to the above equation, we get P is equal to mu minus 1 into, normally for glass mu, the value of mu is 1.5 into 1 by R1. It is having a fixed value, but the value will be positive minus 1 by minus R2, isn't it? Which means 1 by R1 plus 1 by R2. Using applying sign convention and the value, we will get 1 by R1 plus 1 by R2, which means power of convex lens is positive. Power of convex lens is taken as positive. Now let us see for a, what is the case for a concave lens. Now imagine you have a concave lens. Your optical center. Now this concave lens is also made from spheres, isn't it? So let us take the first refracting surface, and this is the sphere. First refracting surface, which means R1, and so this is the center of curvature, so R1 is taken in the direction opposite to the direction of light, isn't it? Which means for a concave lens, R1 is, the value will be negative. Now let us take the next refracting surface, and for the next refracting surface, what is this for? R2 is taken in this direction, which means R2 is taken in the direction of light, so it is positive. So when we substitute the value of R1 and R2 along with the sign convention, what happens? Power is equal to mu minus 1 into, you get 1 by minus R1 minus 1 by R2. So definitely the power will be having a negative value, which means power for a concave lens is negative. So if your eye specialist suggests for you to use a lens which is having negative power, means they are using a concave lens, else you will be using a convex lens. Okay. Now let us go to the next topic in this video, that is equivalent focal length and power of lenses in contact. Equivalent focal length We are going to say about combination of lens. So let us first see what we mean by equivalent lens. Equivalent lens. A single lens which forms image of an object at the same position as formed by the combination of lens is called a equivalent lens. Imagine you have a convex lens which forms an image at a position, and if instead of this single convex lens you are using two lenses, combining two lenses which are placed very close to each other, which are coaxial, and if you are getting the same image at the same point, then the first convex lens and this combination of lens can be said to be a equivalent lens. So we are going to derive the expression for combination of two lenses, and we are going to find out what is the power, total power for such a combination. So imagine you have two lenses L1 and L2 which are placed very close to each other in a coaxial, which means along the same axis, there is no space between the lens. Now when we are deriving this relation, we are using the same method or concept that we used for deriving the lens maker's formula. There we consider two separate spherical surfaces. Here instead of two separate spherical surfaces, what we are considering is two lenses which are placed very close to each other. So what is happening? Imagine you have an object O placed on the principal axis of the lens, and the light ray from the object incidents on the first refracting surface of the lens L1. Now the lens after refraction forms an image at I1. Okay, so the object distance for the lens L1 is U, and the image distance for lens L1 is V1. Now we have the second lens placed in contact with the first lens, isn't it? So the image I1 acts as a virtual object or an imaginary object for the second lens L2, and we will obtain a final image at I. Now we won't be able to see I1 as I told you before. We will be able to see only the final real image, that is I. So object is kept at O, final image is formed at I. But there is a real image or a virtual object I1 somewhere in front after I. Okay, and for the final image V1 will be what? V1 will be the object distance, because it is the I1 is the object. I1 is the object in the case of lens L2, and V will be the final image. Okay, so let us find out what is the focal length for such a combination. So for lens L1, object distance is U and image distance is V1, and F1 is the focal length of lens L1. Focal length is F1. So using the lens formula, for L1, that is lens L1, we get 1 by V. Here 1 by V comes 1 by V1 minus 1 by U is equal to 1 by F1. This is equation 1. Okay, now what is the next step? The image formed by lens L1 acts as a virtual object for lens L2, and hence for lens L2, object distance will be what? Object distance will be V1, image distance will be the image distance for L2 is V. So using the lens formula we get 1 by V minus 1 by V1 is equal to 1 by F2. This is equation 2. So combining equation 1 and 2 we get 1 by V1 minus 1 by U plus 1 by V minus 1 by V1 is equal to 1 by F1 plus 1 by F2, or we can write 1 by V minus 1 by U is equal to 1 by F1 plus 1 by F2. Now what is 1 by V minus 1 by U? It is the focal length of the given length, isn't it? So we can write at the end 1 by F is equal to 1 by F1 plus 1 by F2. This is the equation for, this is the effective focal length for two lenses if they are combined. So instead of two lenses we are using n number of lenses, then the above equation can be written as 1 by F is equal to 1 by F1 plus 1 by F2 plus etc. 1 by Fn. Similarly, power for combination of lens will be P is equal to P1 plus P2 plus etc. Pn. I hope this derivation is clear to you. Thank you.